All right, we'll go ahead and get started. This is internal stresses and deflection, part one. Today's agenda, we're going to cover internal stress review, what that means, bending of a beam, curvature and deflection, longitudinal strains and stresses. Hopefully remember those from the first semester. We'll take a close look at bending and then talk about the geometry and its importance. Quick refresher of stress. So stress is the internal reaction or resistance of a body to the forces acting on that body. So in the right, the weightlifter is holding up a very heavy dumbbell. The force is the dumbbell and the body is undergoing a compressive stress. Okay, there are 5 basic types of stress: tension, compression, shear, torsion, and bending. And these are a quick diagram of each. So recall that from the first semester. So hopefully you remember that bending stress is made up of compression and tension. What we don't know yet is why. So we're going to take a close look at that. But you can see that the top of the bending, when the positive bending moment happens, top of the beam is in compression, the bottom is in tension, and that's shown by the arrows in the cross section. Taking that same three-dimensional view and looking at it in an elevation view from the side, you can see those arrows, again, tension in the bottom, compression in the top. Also need you to remember that stress and strain are related. So you remember the materials graph here. We talked a lot about it, also tested over it. So stress and strain are related. So as something elongates, it increases in stress. As the stress increases, it gets longer or shorter. Those things happen together. So I want you to consider a beam in bending. So we exaggerate a lot and make this curved beam that looks like this. The top fibers are closer to the center of the bending radius or the bending center, if you will, and the bottom fibers are farther from the bending center. And the green highlight there is what we call the neutral axis, and it's between the top fibers and the bottom fibers. So if I exactly copy that green highlight and move it up to the top fibers, you can see that the green highlight is actually longer than what's left of the top fibers by the delta on each end. So what we're saying is that the fibers on the top used to be, when the beam was not bending, when the beam was straight, they used to be the same length as the fibers at the neutral axis, but now we're asking them to be shorter. So we are compressing them or pushing them, shrinking them, and therefore we're ending up with stress that's negative or compressive stress because we're causing a strain that's negative. Top segment getting shorter than the neutral axis. If we do the same thing from to the bottom fibers, you can see that, oh, the bottom fibers are actually longer than the neutral axis. So we're elongating them or stretching them and causing a positive stress or tension in the bottom fibers. So when we bend something, there's a neutral axis that stays exactly the same. No positive or negative stress, no positive or negative strain. Top fibers that get shorter, bottom fibers that get longer. That's what causes distress. So then that begs the question, if you look at the whole cross section, what's the average axial stress across the beam that's in bending? Answer is 0 because the compression and tension cancels each other out 100%. So if you look at the whole cross section, the axial stress averages 0. So you recall we calculated a lot of internal bending moments, but we didn't really think about what that meant. So we're going to do that right now. Okay, so bear with me. I'm just going to derive this. I know that's uh, not easy or fun, but take a look at the picture, and we have a stress block, if you will, that's in compression. So we're calculating now the volume of that stress block, so the base times height, and the h over 2 is half of the height of the beam. And then we have FC, which is the width there. So we have a triangular block, so we take FC times B times h over 2, and then all of that divided by 2 because this is a wedge, not a rectangular prism. And if you do the math up there in the top, you'll end up with the total force in that wedge block is Fc times BH over 4. Just hold on to that for a second. All we did was calculate the volume of the block. If I do the same thing on the bottom, the tension wedge, you can see that we get exactly the same answer but with an Ft instead of an Fc. So again, nothing crazy there, but we end up with equivalent concentrated load Fc and equivalent concentrated load Ft. Go ahead and locate those concentrated loads where they would be for a triangular uniform load. We know that that's 1/3 from the larger end, so 1/3 from the top or the bottom respectively, and I put them something like that. So let's take a look at that. Remember what moment represents is force times distance, right? So think about that. Force times distance, we have the forces, we know what the distances are, so let's see what happens. The only thing I want to point out on this slide is that we know what the distance is, 1/3 from the larger end. So it's 2/3 from the smaller end. The smaller end happens at the center of the neutral axis, and we know that height of the triangle is h over 2. So 2/3 times h over 2 gives us h over 3 from the center of the stress to the neutral axis. Um, There's a diagram that represents that. So if I multiply by h over 3 times the force that I already calculated, I end up with this nasty looking equation, Fc times bh squared over 12. So keep a hold of that in your memory. So I end up with the same thing, right, on the top and the bottom. One is a moment from the compression, one is a moment from the tension, both acting about that neutral axis. You see they're both in the same direction, so we're going to add them together. So I add them together like this. You can see that I have taken the FC and the FT and I've just made them F without the C and the T because we know that those in a rectangular cross section are equal and opposite. So I'm just going to call them F and not worry about the direction because we added it in the right hand rule. So I end up with FBH squared over 6. That's a lot easier of an equation. And here's the magic. Structural engineers like to coin the term section modulus. That's a geometric property of a cross section. And we like to use the section modulus representing everything but the F or the stress. So BH squared over 6 is S or the section modulus for a rectangle. So S equals BH squared over 6. So if you joined us in class, hopefully you did. If you didn't, catch up with a fellow classmate, student. We measured the deflection of a yardstick, the flat-wise bending and the height-wise bending to see what the difference was. I think it's pretty remarkable, so make sure you check it out. So the question is, why does a group of yardsticks deflect differently than a yardstick by itself? Or rather, why does 4 yardsticks stacked on top of each other deflect differently than 4 yardsticks bolted together? And that's all because of the moment of inertia or the change in the section modulus. Instead of having 4 individual yardsticks, we're creating one thicker yardstick that is stronger because it's acting compositely. So I told you that's the moment of inertia. So what is the moment of inertia? Um, that's confusing, right? So how about inertia? I think most of you have a concept of what that is. So what if you tried to move me? It would take a certain amount of force just to move me, right? Just to accelerate my mass, barring any other forces that I tried to use to stand still. You agree with that? Yeah? How about if you placed a baseball in front of a high-speed train? It would baseball would start moving with the train and the train would almost feel nothing, right? Okay. What about if you threw a train or you threw a baseball at a train? Again, nothing would happen, right? The train wouldn't move and the baseball would bounce off the train. And again, it would not really have a reaction. So the moment of inertia is the rotational equivalent of inertia. It's the ability of the mass to resist rotation, or the ability of a cross section to resist bending. The same way that the train has a lot of inertia because it's hard for that baseball to cause it to move. The baseball doesn't have as much mass or as much momentum, so it doesn't make a dent in causing the train to move. Um, so all loading conditions equal, the higher the moment of inertia, the smaller the beam's deflection because it has a greater resistance to bending. So um, what do we use the moment of inertia for? Well, here's the equation for a deflection of a beam, the buckling of a column, and the radius of gyration. So don't worry about that last one, but deflection of a beam, so the higher the moment of inertia, the smaller the deflection. In the buckling of a column, the higher the moment of inertia, the higher the buckling capacity. All of those are good things. So moment of inertia helps us out a lot. Technically speaking, the moment of inertia is the second moment of an area about a given axis. I know that's overwhelming and there's the integral that it equals to, but don't worry about that. We're not going to use an integral. We're just going to think about this conceptually, and I'm going to give you some pretty straightforward formulas to use to calculate this. So here are the three formulas you might need for this class. If you have a rectangle, bh cubed over 12, you notice that's pretty close to bh squared over 6, which was the section modulus. So pretty similar. We'll talk a little bit about why those are similar or different in a second. If you have a circular cross section, it's pi r to the fourth over 4. Triangular cross section, bh cubed over 36. So nice thing about the moment of inertia, not all beams are rectangles, right? We use a lot of wide flanges, or those I-beams, as you like to call them. So the moment of inertia, or I, for complex shapes can be determined by combining simple shapes. So you can add them about like axis. You can add the simple shapes to get a complex shape. You can also subtract them. So if you have a hollow rectangle, you can use a bigger rectangle and then subtract a smaller rectangle in the middle to get the moment of inertia for the complex shape. The catch is they have to be about the same axis. They have to be centered on the same axis. Here's a quick example where I have a hollow rectangle. So I have the hollow rectangle on the far left, and that's equal to the larger rectangle minus the smaller rectangle, or minus the center rectangle. So you can see how that works. Um, really no problem. It's just one minus the other. So you calculate the moment of inertia for the two solid rectangles, subtract the center from the large, and you end up with the total. Here's another example where you have the I shape, or the wide flange beam cross section. So you have the large rectangle minus the two side rectangles. Notice that those aren't symmetrical in both directions. They're not about the same center, but in the um, or in the y-axis, or about the x-axis, rotating about the x-axis, the center of all the rectangles are the same, so that's a good thing, and we can totally subtract those because their centers are on the same axis. Another way we can do that is by um, adding the two flange rectangles to the center rectangle. Now the trick here is that those two flange rectangles are a little more complicated because the center of each of those rectangles is not centered on X bar. So we have to be careful that we need to shift the axis, okay? That's why I included the D and You can shift the axis, but why when we have an easier way to do it, right? So let's do it the easier way. So the moment of inertia I told you before is really similar to the equation for the section modulus. Instead of bh cubed over 3, I'm sorry, bh cubed over 12, it's bh squared over 6. So I'm just saying that the I is equal to the S times H over 2 for a rectangle. So S times H over 2 will take that section modulus and give you the I moment of inertia. The only difference. You can use either one in the equations. Just make sure if it calls for S, use S. If it calls for I, use I. But stress and bending equations can use both. So if I want to solve for the stress in a cross section, I can say that F equals M over S. So M is the internal bending moment and S is the section modulus. We know that the relationship between section modulus of moment of inertia from the last slide. So if I want to use I instead, I can say it's M times H over 2 all divided by I, or MC over I, what structural engineers like to use, where C is that distance H over 2, or better known as the distance from the neutral axis to the extreme fibers on the top or the bottom. So here's a better visual of that. We have a rectangle and we have stress at the top and the bottom, and C is the distance from the neutral axis to the extremities. In this case, it's the same on the top and the bottom. For the case of a triangle, C is not the same, so be careful when you're using the triangle. The C has to be adjusted whether you're talking about the top or the bottom.